Okay, we're going to go ahead and look at 17.4, which is solubility equilibrium. And solubility equilibrium deals with the equilibrium that deals with the dissolution or precipitation of ionic compounds. So talking about an ionic compound and how much or how little it dissolves or dissociates into its ions. So we can make a prediction about the amount of a substance that's going to actually dissolve. Which is very similar to what we did before. We learned about what will dissolve and what won't. When we talk about our aqueous reactions, we deal with our solubility rules. It ties right in with there, and this is kind of the last part of this chapter. So we talk about then the solubility product constant, or our KSP. Okay, this is where we're dealing now with strictly the equilibrium. I'm talking about here with our solid saturated solution. So if I have this solid saturated solution of BaSO4, remember, so that is saturated means that you have all of the possible solid that I can dissolve in a solution. Okay, my equilibrium is only going to be expressed depending on the concentration of my ions, because the BaSO4 in this example that we're looking at is the solid. Well, solids don't go in equilibrium. So we talk about, for example, like barium sulfate. Okay, BaSO4, it is going to dissolve into or dissociate into its two ions because it's an ionic compound. Ionic compounds fall apart when they're in a solution. My KSP is another K here. This is my solubility product constant. Is only my concentration of my Ba2 plus ion and the concentration of my SO4 2 minus ion, and that would just be because my BaSO4 is a solid, so it's products over reactants. So my reactant isn't part of my equilibrium. Okay, this is dealing again with only the solid and its saturated solution. Okay, when we're talking about a KSP, that's telling us how soluble the solid is in water. The smaller the number, that means then that only a small number dissolves. So it's kind of like our other Ks. Okay, we're talking about, and it doesn't go really a lot to the right if I have a small K. Same thing here. I don't have a lot of it going to the right, which means I don't have a lot of ions, which means not very much of it actually dissolves. So looking at an example here, we're going to write the solubility product constant for CaF2 and look up the corresponding KSP in Appendix D. Again, Appendix D has all of those K values from before, but now we'll look at the flip side of that Appendix D page and we're looking at the KSP, or the solubility product constant values. So I write my reaction, which is going to be CaF2. It's going to break apart into Ca2 plus and 2F minus, because I have two F's. It's not going to fall apart into F2 because that means they were bonded. I don't have F2 bonded together. I just have two F ions. So that means that my K, or my KSP, is equal to the concentration of my Ca2 plus times concentration of my F minus, and my F minus is squared because it is two of them. Look up my KSP in the back, and it'll tell me that is 3.9 times 10 to the negative 11th. So not a whole lot of that CaF2 is going to actually dissolve. Okay, solubility in KSP, it is important to distinguish between solubility and the solubility product constant. Okay, so solubility is the amount of substance that dissolves to form a saturated solution. Okay, solubility is in grams per liter or moles per liter, so it's kind of like a concentration here. And solubility can change as the concentration of my solutes change. So if I have more than one ion in solution, or more than one ion of my solute there, then I can change the solubility of something as the amount of solute that I have in there changes. Okay, now KSP is a little bit different. This is where you have the equilibrium constant that is a measure of how much solid dissolves to form a saturated solution. It's an equilibrium constant. These only have one value for a given temperature for an ionic solid. So for one solid, at one temperature, these have one value, where solubility changes by temperature changing. We have those solubility graphs we looked at before where you have the lines mostly going up because solubility increases as temperature increases. Well, KSP is only for one temperature with one ionic solid. It is possible to use a KSP value of my salt to calculate my solubility, and to convert from one to the other, what we do is you go from your solubility, which is usually in grams per liter. I go to molar solubility, which is just what it sounds like, in moles. So that would be so many moles per liter. Well, then I go to my molar concentration of my ions, So the ions themselves, like Ca2 plus or F minus, and then I can use those ions to figure out my KSP using my expression. So really all solubility and KSP have in different is one is for one particular temperature and the other can be is in reference to many temperatures, but they really kind of have the same basic units. Okay, if you're going to go back the other way, I could use my KSP expression and I can figure out what X is because X is going to be the molar solubility of my salt. Then I can figure out the concentration for my species, which would be all of my ions, and then I use those concentrations into my expression and you solve. It's really not all that hard. Sometimes it's just annoying about what goes where. And you have that little diagram there down at the bottom, which is pretty much telling you the same thing. They deal with the same types of measurements. There's a little bit different as to how the units are and what they actually specify at a particular temperature or many different temperatures. So let's go ahead and try an example here. I have solid silver chromate added to water. Some of my solid remains at the bottom, which means I have a saturated solution. My mixture is stirred to make sure that I have equilibrium achieved, and between my undissolved solid and my solution, I analyze it and I figure out that my silver ion concentration is that 1.3 times 10 to the negative fourth. If I assume that my silver chromate dissociates completely in water and there's nothing else going on, I want to calculate the KSP for this particular compound. So let's look at the reaction overall. Okay, I've got my silver chromate, Ag2CrO4. It's going to fall apart into Ag plus and CrO4 2 minus. Now I'm going to have two Ags. Now I want my KSP, which means KSP equals concentration of my Ag plus squared times concentration of my CrO4 2 minus. So I need to know these two concentrations so I can plug them in and get my K value. Well, they give me one of my concentrations, which is nice. So I know that my Ag plus concentration, they tell me the problem, is 1.3 times 10 to the negative fourth. Well, if I want to know my concentrations for CrO4 2 minus, it's actually fairly easy because I'm going to make two Ag pluses, but I'm only going to make one CrO4 2 minus. So a little bit of stoichiometry tells me that the chromate ion is going to have half as many ions as my silver. So I take my silver and I divide by 2. Which is going to give me 6.5 times 10 to the negative fifth. Now all I do is plug my numbers in. And I'm going to have my KSP is equal to my 1.3 times 10 to the negative fourth times 6.5 times 10 to the negative fifth. And don't forget that your Ag is squared. And my KSP is going to be 1.1 times 10 to the negative 12th. And if you look it up in the back of the book, it should tell you that exact same number. The last one, the KSP for CaF2 is 3.9 times 10 to the negative 11th. If I assume that CaF2 dissociates completely and there's nothing else going on, I want to calculate the solubility of CaF2 in grams per liter. So I've got my CaF2, I break apart into Ca2 plus and 2F minus. I want to know the solubility of this in so many grams per liter. Well, I do know that for KSP, it's going to be my Ca2 plus times my F minus squared. And they tell me my KSP value, which is 3.9 times 10 to the negative 11th. So I could figure out how many grams per liter, like a concentration of CaF2, if I knew my other concentrations of my ions. Well, you kind of do. If it dissociates completely, that means whatever forms is equal to the amount that you dissolved. So that's kind of like a little bit of equilibrium here with an ice table. Okay, it's going to break apart into X and 2X. It's all going to shift this way because it's dissociating. It's 2X because there's two of them. So what I do is I plug it in. I've got X times 2X squared, and I don't care what this is because this is a solid, so it's not in my equilibrium expression, equal to 3.9 times 10 to the negative 11th. 4x cubed equals my number. Take my divide by 4 and take the cubed root, or to the 1/3, and I'm going to get x equal to 2.1 times 10 to the negative fourth. Now this is the concentration of my ions. So this is how the concentration of my ions, which is so many moles per liter. So that's going to be how much my Ca2 plus, well, it's 1 to 1. So whatever amount of Ca2 plus that I formed and dissociated is how much CaF2 in moles that I had. So this is also my concentration of CaF2, but I want it in grams per liter. So all I do is I take my 2.14 or 2.1 times 10 to the negative fourth, take it times my molar mass, which is 78.1 grams, because that's my molar mass of the CaF2. That's going to give me 0.016 grams per liter.